Hello and welcome to yet another fun-filled video about the topic of mathematical differentiation. So this is the fifth lesson of chapter 12, which I'm going to talk through about differentiation. So let's start off with, as you can probably guess, the 4 space retrieval warm-up questions. So here they are. So yet again, what I'd always suggest is to freeze the video and have a go at these questions yourselves, and then once you've got your solutions, press play and see if you've got them correct. So let's have a go at the first question and see how you've done. So question 1, prove that for all real values of x, that 3x squared plus 6x plus 5 is greater than 0. So the way I'd suggest approaching this one would be to complete the square. So here, we can factorise out the 3 and say it's 3 lots of x squared plus 2x plus 5. Okay, so we're just equating this bit here. So we're saying that 3x squared plus 6x plus 5 equals this. In fact, just to make it clearer, I'll write this down next to it. So it equals 3 lots of x squared plus 2x plus 5. So now we can complete the square on what's inside these brackets. So that's going to be 3 lots of, in big square brackets, x plus 1 all squared. That'll give us an extra 1, which we don't want, so minus off that 1. And then the plus 5 on the outside. So now expand it all out. We have 3 lots of x plus 1 all squared. 3 times minus 1 gives us minus 3, and of course the plus 5. And so simplifying down, we get 3 lots of x plus 1 all squared minus 3 plus 5 gives us 2. So let's just think of each term in turn. So we've got x plus 1 all squared, and so obviously any value squared has to be at least 0. The smallest it can be is 0. And also we have for 2, and 2 is obviously greater than 0. And that's true for all values of x which are real numbers. So therefore, we can say that the original expression, 3x squared plus 6x plus 5, must therefore be greater than 0 for all real values of x. And so that's our proof complete. And question 1's wrapped up. So let's have a look at question 2 now. For question 2, we need to solve the inequality 3x squared plus 10x minus 8 is less than or equal to 0. And so we can factorise this expression here, and we get 3x squared, obviously. Think of 2 numbers that multiply to give us minus 24, but add up to 10. You should eventually get that that's positive 12 and minus 2. So we can partition the 10x into a plus 12 and a minus 2x. Then minus 8 less than or equal to 0. So this bit will factorise. We can factorise out a 3x, and we have in brackets x plus 4. Then over here we've got minus 2, then in brackets x plus 4, and again less than or equal to 0. So we've got this x plus 4 bracket twice, so we can then put inside 3x minus 2 into its own bracket. So we have 3x minus 2, x plus 4, less than or equal to 0 rather. So what I'd suggest doing here, if you want to solve an inequality which is quadratic, just to do a little sketch of a graph. And so if we do this here, just have y and x. So it's a positive quadratic, so it's going to be curving upwards. One critical point is going to be where x is 2/3. When x is 2/3, this bracket will be equal to 0. And the other point will be minus 4, which will give this bracket equal to 0. And so it's going to be a positive quadratic going through these points. So not the best sketch, but hopefully you get the idea. So we want this to be less than or equal to 0, and so we're after the region of this curve, which is below the x-axis. So we're wanting our x to be between -4 and 2/3. That's the region for which 3x squared plus 10x minus 8 is less than or equal to 0. So therefore what we want in here for our values of x is for x to be greater or equal to -4, yet also no greater than 2/3. And that's just done for question 2. Question 3, differentiate y with respect to x. Now, we've got here a fairly strange looking function, so it's not in the usual form. So the first trick here is to rearrange this into a form which is much more familiar. So if we divide through by x, we get y equals 2 minus x cubed all over x. And then if we just partition out the terms on the top, we get y equals 2 divided by x, which in index form we can say is 2x to the power -1. And then the second term, x cubed over x, we can say is x squared. So then differentiating this with respect to x, dy by dx, we do this piecemeal for each term individually. So this first term here, the -1 will go to the front and multiply the 2. So we get -2, and the power drops by 1. So it becomes -2. The 2 here, again, in the same way, drops to the front, so we get -2x. But the new power of this x will drop from 2 and become power 1. So obviously if it's to the power 1, we don't need to include that. So our final answer is dy by dx equals -2, x to the -2, minus 2x. Lastly, for this warm-up, we've got here a quadratic involving k. K is a constant, and we're told this has got no real roots. So we need to prove, therefore, that k is greater than or equal to 0, but less than 3/4. So the clue here is that this quadratic has no real roots. And so what we need to realise from this is, if it's got no real roots, then this tells us that the discriminant must be less than 0. And so this discriminant is going to be b squared, which in our case is 4k all squared, minus 4 times the coefficient of x, which is k, times the the constant term at the end, which is 3. All of that needs to be less than 0. So let's simplify this. 4k all squared is 16k squared, and 4 times k times 3 gives us 12k. We don't have to, but what I'd suggest is, because we have a constant factor of 4, we can divide through all of this by 4, and we get 4k squared minus 3k is less than 0. Now let's factorise out the k. So we have k brackets 4k minus 3 is less than or equal to 0. Now again, what I'd suggest is to think of this as a function of k itself. A function of k, as shown here, will itself be a quadratic, and so the discriminant gives us a quadratic function within this original quadratic. So if I just show you this sketch to help clarify it, if we imagine k is moving along, and up here this is the function of k, which is 16k squared minus 12k. So I just call that our function of k. And so we're wanting this to have no real roots. And so what we want here is where k is less than, so the discriminant rather, which is the function, we want that to be less than 0. And so we're wanting the bit of the curve which is below this k-axis. So we're wanting all of this bit here. Okay, so we're wanting k to be between 0 and this value here relates to 3/4. So therefore what we need is for k to be in between 3/4 also greater than 0. However, you might be wondering, if a discriminant is less than 0, how we can have this inequality symbol here. Well, we can. I'm going to explain why. This symbol here, we're allowed it to be 0, but k must be less than 3/4. So essentially, k can equal 0, because if k did equal 0, so just write this down, if k did equal 0, the equation, this equation here would become, just let me write this out, the equation would become, well, kx squared would vanish, 4kx would also vanish, that would be 0, so we'd just be left with 3 equals 0, which obviously isn't correct. So that still has no roots, which is what we want. Which has no solution. So still satisfies our conditions. Because even if k were 0, this would still have no real roots, because this obviously is a nonsense. This would still have no solutions. So that still satisfies our conditions. So just trying to give some clarity as to why this is allowed. Okay, so a bit of an introduction now onto what we mean by an increasing function and a decreasing function. And so the derivative, the gradient function, we can use that to determine whether a function is increasing or decreasing on a given interval. And so just to give you some definitions, an increasing function on an interval between and including a and b is a function where the gradient is less than or equal to 0. Sorry, I keep getting this wrong. Where the gradient is more than or equal to 0 for all x values within this interval between a and b. And so it's increasing if between a and b the gradient is always non-negative. On the other hand, a function is decreasing on an interval, for example, between a and b, if the gradient function, if the derivative, is less than or equal to 0 for all x values within that interval. So I've got a couple of examples for you here. And so this first one is y equals x cubed plus x. As you can see here, this gradient is always positive, sometimes more positive than at other points on the graph, but it's never going downwards. And of course, we could prove that algebraically by taking the derivative dy by dx. So if you wanted to, dy by dx of this function would just be 3x squared plus 1. So x squared is never negative, and 1 is always 1, and so this is always going to be a positive value. So that's why y equals x squared plus x is always an increasing function for all values of x. On the other hand here, this weird quartic graph we have, well, that's a mixture of increasing and decreasing. So if you have a look here, it's increasing. In terms of the graph, it just means whereabouts is the graph going up. It's curving up on the interval from -1 to 0, so it's going up here. However, it's decreasing, it's going down on the interval between 0 and 1. That's where it's going down. As well, it's going down at other parts as well. It's decreasing over here as well, so that's where it's a decreasing function. And also it'd be increasing for all values of x equal to or greater than 1. But what we just picked out here is these 2 points. And so a function can be both increasing and decreasing at different points along its domain, along the values for x. So, just a couple of examples showing you about these increasing and decreasing functions. So we need to show for this function, f of x equal to x cubed plus 3x squared plus 5x plus 2 is increasing for all x being a real number. I'll give you a clue here in case you're wondering, well, how can this help? or how can I help myself to understand this? If you have a look back at warm-up question 1. So as a hint, just check warm-up question 1. This will make sense in a second. So warm-up question 1 will help with part of this question. So anyway, what we need to do first of all is to take the gradient function, to differentiate it. So f dashed of x, this equals 3x squared plus 6x plus 5. Now, if you were to return to question 1 on the warm-up, this here is an expression which we already proved has to be greater than 0. In case you don't want to turn back through your notes, you want me to do this again for you, let's do it anyway. So f dashed of x, so we get 3 lots of x squared plus 2x plus 5. Complete the square on what we have in the brackets now. So we have x plus 1 all squared minus off the unwanted 1 plus that 5 on the end. That's the same as 3 lots of x plus 1 all squared minus 3 times 1, which is minus off of 3, plus 5. And finally, we get 3 lots of x plus 1 all squared plus 2. Now I'm going to attempt to be quite lazy here. This might backfire if I can't quite manage it, but rather than writing pretty much the same thing as what I wrote for warm-up 1, let's see if I can just copy and paste what we had from before. So bear with me a moment, let's see if this works. You can laugh if it doesn't. So let's just nab this, so copy and paste. Hey, not so bad. So yeah, like I said before, this part here is always going to be non-negative, and 2 is always going to be greater than 0 for all x greater than r. So therefore, this thing here, which is f dashed of x, is always going to be greater than 0. So just have a slight tinker to what I copied and pasted. I can just simply say here that therefore, f dashed of x, which equals this, is going to be greater than 0, hence f of x is increasing for all real numbers taken for x. So we've proven what we needed to, just using warm-up question 1 as our way into it. Okay. So question 2, find the interval on which the function f of x equals x cubed plus 5x squared minus 8x plus 3 is decreasing. In the same way, as a hint, I'm going to give you warm-up question 2, because that'll help. My pen cursor seems to be going a bit mad. It says it's a eraser, but it's obviously not. So have a look at warm-up question 2 in a second. Okay, so again, we find out if a function is increasing or decreasing by taking the derivative. So let's do this first of all. We have f dashed x equals 3x squared plus 10x, when we bring this 2 to the front and drop the power of x, minus 8. Now, I did say about warm-up question 2, and so we can take this a bit further using warm-up question 2. So just freeze us for a second, write that down, and then we can use what we've done previously in warm-up question 2 just to help us out with this. So we've got this here, so let's just copy this across. Wasn't liking that. There we go. So just to try and show you the link with the warm-ups. Sometimes the warm-ups don't relate. In this case, I want to make a point that they do. So always just be thinking about how your set of notes relates into a bigger picture. And so let's just tinker this slightly. So we can say that f dashed of x equals this, equals that, equals this. Take this out for a second. So all I'm doing here is just showing you whereabouts this function ends up going if we were to factorize it. And so we've got this. And so it's going to be decreasing where this is going to be less than 0. So we can write this down now. So f dashed x is decreasing for when this expression here, 3x minus 2, x plus 4, is less than 0. Okay, so what we have here, what we had before rather, is a sketch. So just to do a sketch graph, so just going along like this. So this quadratic here will have critical values when x is 2/3 and also at minus 4 like we showed earlier. So let's see if I can just do it going through these points. Ooh. Just forgive a terrible sketch, hopefully you see the point. So yeah, we want this to be decreasing when this is less than 0. And so it's going to be a decreasing function between these values of x. It's decreasing in between minus 4 and 2/3. So we can therefore say that therefore f of x is decreasing on the following interval. And I'll show you about interval notation as well. It's decreasing on the interval now we can use these squared brackets and say minus 4 comma 2/3. Now I'm just going to explain why we use these squared brackets. The squared brackets mean that it's including these limits, and so f of x is decreasing, the function is decreasing on this interval from minus 4 to 2/3 inclusive. Okay, just to have a little tinker, we can just say that's actually f of x. So because f dashed x is decreasing between these two values, that proves that the function of x is decreasing on this interval. So why including minus 4 and 2/3? Why not being greater than minus 4 and less than 2/3? If I just take you back to the original definitions of the increasing and decreasing functions, you see it's increasing or decreasing for when x is between a and b, but we can use these squared brackets as shown. And so whenever we're giving a decreasing or increasing interval, we can include these square brackets in our notation. And so that's a couple of examples which I've done with you. So what I want you to try now is sum yourself if you can do in a second. But before we do that, let's just have a look at something which will make more sense in the next lesson. But I'm just going to give you a bit of a head start on it. It's second order derivatives. So you've seen now that functions can be differentiated. So you can start with a function, which is y equals f of x. You can differentiate it once. That tells you the gradient function. So if you differentiate it once, it tells you the rate of change of a function. The rate of change of a function is the gradient. And if you differentiate again, that tells you the rate of change of the rate of change. So if the rate of change is the gradient, the second derivative tells us the rate of change of the gradient. Okay, so I'll just drop this in for you. The second derivative tells us the rate of change of the gradient. So this concept we're going to use next lesson. But I'm just going to show you in terms of how to actually compute the second derivative. It's very simple. And obviously we've shown that f dashed of x is the gradient. You could do a third derivative as well, which for notation would be d cubed y over dx cubed, which would be the rate of change of the rate of change of the gradient, and so on. So let's have a look at how we'd work this out. So I want you to imagine that we've got this function y equals x squared minus 3 all over root x. So first of all, let's find dy by dx, the first derivative, part b, the second derivative. This, by the way, is just notation. We're not actually squaring a d or squaring an x. It's just how we write down the second derivative. Okay. So first of all, what I'd suggest we do is we rewrite this function in a more manageable looking way. So let's just do this in an index form and say we've got y equals, well, x squared divided by x. X square rooted just means x to the power of a half. So if we were to just take this and do x to the power 2 divided by x to the power half and use the law of indices, we'd have x to the power 1.5, which is 3 over 2. And then 3 divided by root x, well, square root of x is a half. 1 over the square root of x will therefore be x to the minus half. So this is a more useful form for us. Using this form here, we can take the derivative of it by the same process as before. Bring the power to the front, so 3 over 2 x, and take 1 from this original power. So 1 less than 3 over 2 is just 1 over 2. This here, this power comes to the front, so the minus 3 gets multiplied by the minus a half, so we end up again with positive 3 halves x, then minus 1 from minus a half minus 1 gives us minus 3 over 2. Now for the second part, for part b, we do the second derivative by differentiating the first derivative. And so d squared y over dx squared I'm going to give you a bit more notation here. We can say that this is the derivative. Now, because this doesn't involve a y in it as such, and for some questions it might not be a function of y, we can actually leave the y out at the top and say it's the same as differentiating this here. So if we were to differentiate again the function we just ended up with, and apply the exact same method for when we differentiate, we get the second derivative. We're literally doing the derivative twice. We're differentiating twice. And so in the same way as before, we take this power, bring it to the front, so 3 over 2 multiplied by a half, that becomes 3/4. And the power of x becomes 1 less. So 1 off a half becomes minus a half. And this one here, minus 3 over 2 multiplied by 3 over 2, that gives us minus 9 over 4. And the new power of x, minus 3 over 2 minus another 1, that becomes minus 5 over 2. And so in summary, we have a function, dy by dx, we differentiate it once. If we differentiate the first derivative, that gives us the second derivative. And that will tell us the rate of change of the gradient, which will come into play next lesson. I hope you found those examples useful. You'll find it much more useful when you practice yourself, which brings me on to this point here. Have a go at these suggested exercises if you can. Exercise 12G and 12H. Okay, if you practice these, if you do the questions and check the solutions out, and then email me or drop a question in the comments if you're not getting it, That will help you much more than me just talking through. So listen and then apply by doing the exercises. Okay, so happy hunting. Hope those exercises make sense. If not, you know how and where to contact me. Good luck, and I'll see you and hear from you hopefully soon. Okay, bye for now. Thanks for listening.